Hello again. This is the second part of the previous video about the integration of rational functions. Here we will present an example where the function that we want to integrate is a rational function, and we want to find the definite integral of this function. The first part, as we saw in the previous video lesson, we need to ensure that the hypotheses of the fundamental theorem of calculus are met, meaning that we need to have a closed interval and a continuous function inside this interval. And as you can see, these two hypotheses are met. So now we need to know the integral of this rational function. Let's call to the integral of this rational function capital I. And now we need to find this function capital I. The first auxiliary calculus is about the comparison between the powers of the two polynomials. And as we can see, the powers are equal, meaning that we need to perform a long division. So let's do that. And as you can see, performing the long division, the quotient of the division is 1, and the remainder part is minus 4x minus 2. So, using these two new polynomials, we can rewrite the division as a sum between the quotient and the division of the remainder part by the capital Q. So we will obtain this using this formula. Capital P over capital Q will be equal to small q plus capital R over capital Q. Then the function capital I can be written as this: the integral of 1 plus minus 4x minus 2 over x squared plus 3x plus 2. And then we can split this integral into two integrals, and we have these two integrals here in this expression. The second integral, as you can see, is the case 2 of the previous video lesson. So now we need to write this second integral as the function as rational as partial fractions. To do this, we need to factorize the capital Q polynomial. To find the factors, you can obtain the zeros of this polynomial. So, doing this, we will obtain the zeros as these. And the zeros are minus 1 and minus 2. So we can write the capital Q polynomial as the multiplication of the two factors x plus 1 times x plus 2, meaning that we have two factors which are linear factors. Then the partial fraction that is related with linear factors is the constant by the factor. Then we have a1 over x plus 1 plus b1 over x plus 2. Now the idea is to obtain the constants a1 and b1. So, solving this equation, we can write an equivalent form as this. And now, comparing the coefficient of both polynomials, we can say that minus 2 will be equal to a1 plus b1, and minus 1 will be equal to 2a1 plus b1 as this. Solving this system of equations, of linear equations, we will obtain the constants a1 and b1. And they will be b1 is minus 3 and a1 is 1. Replacing these constants into the partial fractions and then into the last equation that we have here in the left, we can rewrite the integral as this. The integral of 1 will be x plus 2 integral of, and now we replace the division by the partial fractions, and we have 1 over x plus 1 minus 3 over x plus 2. And now, solving this, we will obtain to multiply natural log of the absolute value of x plus 1 minus 6 natural log of the absolute value of x plus 2, and of course at the end the constant c. At this moment we know already the integral of the function that we had at the beginning. Now we need to apply the fundamental theorem of calculus, meaning that the finite integral that we want to evaluate is given by the capital I that we obtained evaluated in 0 and 2. So, replacing the capital I by the expression, and now evaluating this on 0 and 2, we will obtain the following values. Since log of 1 is 0, we can say that the value that we want is this one. And now performing some simplifications, meaning that we use the log properties, we can rewrite the expression into the following one.